from Australia. He just visited me, and he said to me, ¿puedes pasar el anterior otra vez? Then he just visited me, and he went to the field last half an hour before me, and he sent to me this video. For he was really unbelievable. I have seen this many times. You see, it was only 30 millimeters of rainfall in 40 minutes, and then we have all the water flowing. You see the color of the water. Okay, this is enough, and this is coming from the olive plantations. Then we are losing soil all the time. And now the other videos are to show you some of the experiments, because we are trying to find solutions. I spent half of my life trying to understand the process, and the other half of my life as a scientist trying to find solutions. This is our rainfall simulators that we use. Most of our measurements are done first in the lab, then we pass to the field with rainfall simulators or other strategies, and finally we establish plots to have a long period of measurements. My talk will be very complementary to the one of Panos Panagos. He's having a huge view of the whole Europe, and then I work in an orchard, sometimes only with 3 olives, and I want to understand the process, how it works. For example, now that you was watching the rain, okay, most of us, we don't know how big are the drops of the rain. We are talking about the process and we know very little. For example, remember these images of the water flowing through the straw, because we found that upper soil have high erosion rate. If you put only 5% cover of a straw, you reduce 50% of the soil erosion. Okay, if you put 25, you reduce 90% the erosion. Okay, and this is more experiments to try to understand how we distribute the straw. This is mainly for fire-affected land that is completely bare, but also our fields are bare in most of the cases. Then how do we distribute? And we compare different options, like dispatch distribution, inlet lines, inlet of whole field, and so on. Okay, vamos al PowerPoint, por favor. Now I like to start with this, because to explain what the soil erosion process, you need to understand the process. No? The process is this: detachment, transport, and sedimentation of the material. And this means that when we are watching the olive plantations with no vegetation, is not only an effect on the farmer, on the plot, is an effect also in the rivers and in the sedimentation areas. We have a lot of problems in the coastal land where Spain has the most of the investment with the floodings. Valencia lost almost 200,000 cars in the last floodings, and most of the damage were done by the mud, not by the water. Okay? Then this will be my talk, is about soil erosion control. We'll talk a little bit first about the basic concepts, the problem, with some pictures. You will see with the pictures it's very clear. And then some solutions based on nature and culture. Now it's most of the scientists are talking about nature-based solutions, but I like to talk about cultural-based solutions, because humans are here and we developed some strategies that are very efficient, and we sometimes forgot this. We lose like that they are bad people, but I think humans did sometimes good things in the planet. And this will be my conclusions. I tell you my conclusions from the first, because I think the people that, like me, that we have been spent almost 40 years in the field, we know that it's very clear, the situation. The situation is soil erosion compromise the health of the planet and the nutrition of the humanity. And it's not only a question of quantity. It's not a question of how much olive oil we produce. It's the quality of the olive oil. And the olive oil should bring health for the planet and health for the people. If the olive oil is plenty of pesticides, it's not anymore nutritious. Second is agriculture. I come from a farmer's family. Agriculture is responsible for the acceleration of the soil loss. For example, now in Spain, forest fires are on fashion because this summer. My career started with forest fires. And then when I moved to the agricultural land, I found that in agricultural land, every year there is a fire. You know, in a forest, you burn the forest, there are more erosion for 1 year, but after 2 years, we found that the vegetation recovered, and after 4 years, you come back to the previous situation, and then some years later you have much less erosion than previous to the fire because there are less soil to be eroded, which is another factor, how much soil is available to be eroded. And then after 10 years you make an average and it's almost the same. But in agriculture it's not like that. In most of our olive plantations, orange plantations, vineyards, you have all the year the soil bare. And sometimes you plow to put more soil available, or you use herbicides that make a crust on the top and make a lot of runoff to. Then we should know that we are responsible, humans and farmers, policymakers, all of us. But also I can tell you that we have strategies available to control soil erosion. Some of them already known, some others developed by scientists in the last years. And then this means that we have the problem, but we can solve it. And just we need to implement. This is because it's so important, all the policymakers, all the work of the people that is working in management to solve the problem. Okay, we go. Next one, I think this is... Okay. A couple of key questions, a couple of basic concepts. The first one is the cycle of degradation by soil erosion. If you have a soil and you remove part of the soil, you lose fertility. If you lose fertility, you have less biomass. If you have less biomass, your soil will be more eroded. Then it's a circle that is making your land more degraded. This is desertification. And this can start with soil erosion or with loss of fertility or with loss of vegetation. And the other one is very geographical, is the distribution of the soil erosion depending on the rainfall. Let's go to see if this, I'm not sure if this is working. If you hear me? Yes, now you're hearing me. This is the precipitation in different parts of the world, and Professor Schum and Lambing, one of his students, he make a lot of measurements and draw this line. If you are in a desert, you don't have erosion. Erosion is zero. But if you have in an area that the rainfall is 100, 200 millimeters, you don't have enough vegetation, and still the process of erosion is active by water. Then the erosion in growth. And then here you start to have more vegetation, and because you have a forest, the erosion is reduced until it's stable. Okay? Now pay attention to this. It's between 200 and 600 to 700 millimeters. And I'm going to show you now the map of the precipitation in Spain. You know, except the north part or the Portugal or Galician area, all the country is affected by this high erosion rates, natural soil erosion rates. If you remove the vegetation, it's even worse. Like, for example, now in Galicia with the forest fires. Okay, how much rainfall we can have? In one day, this is 24 hours rainfall, and I selected some events. This one here, well, it's a mistake here. It should be 24. It's 1 year ago. This is the rainfall in one day that provoked the floodings in Valencia. You see, most of the areas are in the eastern part of Spain, in the coastal land, because the flow of water water vapor from the sea, from the Mediterranean. You see the name of the cities, and these are the numbers. In all these places, the mean annual rainfall is 400 to 500 millimeters. But in one day, they got this amount of rainfall. Then if we have a soil that is bare, and you have this rainfall, the situation is, I don't know how to come back. ¿Podéis volverla atrás una? Okay, this is Extremadura with olive plantations in an area that they want, like Castilla-La Mancha. They produce half of the wine of Spain with vineyards. We calculate in most of our study areas that every bottle of wine that you drink, 1 kilo of soil is moved. And remember that the bottles of wine are not 1 liter. Okay? And then what do you expect if in this crop, in this vineyard, you have a rainfall of 600 millimeters in one day? then you will have a lot of sediments moving. In fact, you can see also some another type of erosion, which is tillage erosion, okay, the different colors of the soil. This is, I got to use very little images from olives on purpose. I don't want to come here from Valencia to tell that people from Andalusia is wrong. I prefer to tell you we are very wrong and don't make our mistakes. This is Valencia citrus plantations. Do you think this is protecting the soil? These trees, they have only 6 months. See the evidences of soil erosion. We calculated in one of those places, okay, we calculated more than 100 tons in one event. You say, well, this is impossible, 100 tons in one day. You say, yes, look at that, this is one day. Almonds. What we can expect? This is not the agriculture that will solve the problems of the planet. And then when the runoff is concentrated and you have gullies, then the process is almost impossible to stop. And then it's not only a question that the soil is lost in the field and you need to use more fertilizers. And remember, the fertilizers are not so good. They produce a lot of pollution. They are expensive for the farming. We need to try to have a soil that will be healthy, and there will be, don't use, at least not chemical fertilizers. But then this is one example of the impacts of a big thunderstorm, and the water that you see in the river is not clean, it's very dirty. It's having more than 10 grains per liter. We measure it in the Dana, more than 100 grains per liter. It's really almost mad. And this is what makes that all the infrastructure is being removed officially. Okay. Well, let's go to see some pictures. Apricots, recently planted, and then we have only 16 millimeters in 15 minutes. Then it's going, okay, you can see the picture easily. This is, we are using a lot of mechanization, a lot of tractors, moving a lot of soil. And this is one view of the traditional olive plantations in the Mediterranean. We have a big difference here between the Mediterranean coast and Andalusia in the plantation of olive. We have these terraces that protect the soil. They accumulate a lot of soil and they were very, very, very sustainable. But now there is a big change into irrigated, mechanized, industrialized agriculture, like here, that you in Andalusia, you are having mangoes, or you are having avocados in the coastal land, and you are irrigating a lot, no? You are also irrigating, like us, the olives. And then, but you see the change? They put all the rocks, all the stones that they were put it for probably 1 millennia year ago, they put it by hand very well to protect the soil. They collected with machinery, they put 20 meters underneath the soil, and they covered it with soil. And then you have this. Only the process of renewal of the plantations, we found in vineyards that increased the erosion in 100 times. If you take a vineyard and you measure every year from the plantation, the first year you have more erosion than the 9 years later, because the first year you have the soil very exposed, no vegetation cover, very compacted, and then this is the consequences. When I talk with the farmers, they tell me that they do this because it's the only way to mechanize. But they disagree, because later they spend a lot of money to repair this. And what I see is that the farmers that built the terraces, they were illiterate. They didn't know how to write or read. They understand nature better than us, probably, but and now we, as doctors, engineers, geographers like me, we are transforming this beautiful land into this. And the damage can be huge, because this is direct to the river. Then we increase the connectivity of the flows, and then we are transporting sediments, nutrients, organic matter. I remember Panos talking about carbon. You know, we are taking the upper part of the soil out, then most of the carbon. And then from the agronomic point of view, you look at that. I remember that this tree did almost not grow for the next 3 years. And all the roots you see are exposed on the surface. And well, I promised not too many about olive, but I should talk about olive too. Look at the right, no one cover, only the soil on top. Then you have the first little gully here, and then in the next thunderstorm, you have that, which make a big problem for the farmer. Need to cover this with soil, or just allow the gully to grow. Okay, vineyards are no different. Vineyards we found very high erosion rates. The farmers that crop in vineyards, they really don't want any crop any wheat in the middle. They say that we need to preserve the water, we need to plow a lot to preserve the water in the soil, and so on. A new plantation of citrus, like you have seen in olives, moving to very intense, very high density of plants, that they grow very fast, and after 5 years they have almost full production. But if you see the slope is having like bends, and this is because they destroyed the terraces to build this. Now the erosion here is huge. Well, let's go to some research. This is some of the plots that we measured, that we used it in the past. And then our idea is my research team has been investing most of the time to measure the erosion from here till here. The rivers, we are just recently starting to study the flow in the rivers. We were not very focused on the rivers because we have dry rivers. And then these rivers, they work only every 20 years, and then you cannot wait for 20 years. Then we studied the runoff generation here and the sediment transport, and we found that the vegetation was very important. This is an example of Stipa, Esparto. They distribute in patches, and we found that this was in Almeria and Murcia, and then we found that the runoff that is generated here infiltrates in the tussock, in the plant, and then generate a subsurface flow. Then we don't have direct flow, but what we do in a olive plantation is remove this, because the tree does not act as a plant in this way. I see many farmers that they are making now some strategies to collect runoff around the trees. Okay, then we developed this kind of stations in Valencia. It's a lot of work to maintain this and to follow. This, you see the strategy. One of the things that many of the colleagues ask me is, why did you build the plots in different size? You know, why one plot is 1 square meter, 2 square, 4, 16, and even, we have one even bigger. The reason is because the soil erosion is a scale-dependent process. It depends how do you measure, in which size is your plot, this will be the erosion. And then what we do is, because we have 4 measurements of 5, we can make an equation to see which is the sediment delivery ratio. Okay? With Mike Kirby, we published a paper that is called Follow the Curve, Follow the Curve. Because usually in this plot, you can see here, is the 1 meter square. If something moves, it's collected here in the, but here, in the second, some material that is moving here is deposited here. And then the same here. Then when you increase the size of the plot, you reduce the erosion rate. Okay? This is what experimentally is we found. But this is working like that if you don't have gullies. And if you have gullies, the connectivity is very high, and then you increase the erosion, sometimes by 10, by 100, or by 1,000. Okay, then we established different plots with different covers. This was straw. This is herbicides. We use a different type of herbicides, 3 types of herbicides, to check which one it was better. We still are under debate, because these are the results. I don't go to put too many data, because you will see with the pictures the results. We put all the plots together. We had 5 or 4 subplots by 13 types of management. Then the 3 types of herbicides in the first year gave this. Then tillage was much less. This year the rainfall was very low, then tillage was not really supplying sediments. But all the others, we use alfalfa, oats, we use geotextiles, we chipped the branches of olives and we put on the plots, we put a straw, we allow to grow the shrubs, all of them very little. Then this looks bad. Looks bad because most of our farmers, they use herbicides. But in one way, it's a good hope. We know that we can stop soil erosion. It's not something that we cannot control. I come from China. I was in China the whole month of August. And then I was in the mouth of the Yellow River, and it's really yellow, it's plenty of sediments. But they gave me the data, and they reduced in 4 decades by 100. The erosion reduced it 2 orders of magnitude, just because they started to plant in the lowest plateau. And I can give you another example. I have colleagues that they work making artificial floodings in the River Ebro to move the sediments, because there are no sediments in the Ebro River. The mouth of the Ebro River just bring 100 times less sediments now than 100 years ago. If you pass the Ebro River, there is one place that you should visit, which is the only place in Europe that you can cross with a boat without electricity, without it's just with cables. It's unique, and they still pass through the river. You will see the water is clean. This is a miracle, and it's done by the afforestation in the Pyrenees and by the reservoirs. Then it's not a bad news. And now we go to the solutions. One of that I prefer, and I invested more time, is this one. They use chipped pruned branches. In my region, all the farmers, 30 years ago, they burn the branches. They love to burn the branches. In the past, I know that they use it for the sheep or for the rabbits. They use it in different ways. They use it as a fuel. But after the 60s, they started to have this as a residue, and then they start to burn. Also, they burn the straw in the Albufera. In all the paddy fields, they burn the straw. They don't know what to do. And then you see the plots that we use in the rainfall simulator, how after 10 years, see the cover. This is another thing that we learn. It doesn't matter if it's vegetation, or it's a straw, or it's chipped pruned branches. It doesn't matter. You need a cover that will be coming from vegetation, biomass. These are our plots. Then we were using plots, pilot plots. You will see all the experiments that I will show here are pilot plots. We take one control, one with the new management. And then these are the fields that what they do is they bring the branches together and they burn. These are orange plantations. And most of the farmers, especially the small ones, they burn all the branches. For me, this is really unacceptable. But I don't go to blame the farmers. I go to blame myself. Because I'm a professor, I teach, I'm in education, and for 40 years we did nothing to educate the farmers. Okay? Then, if you, instead to do this, you put the branches in the middle, like you do with the olives. You chop them, and then you have this cover and this mulch. In our measurements show that orange produce more than 30 kilos of branches every year. Also, olives is very abundant. And the only problem we have is with vineyards, because the amount of biomass is not so high. Then when you chop the branches, you don't cover fully the soil, okay? And these are some data. Our data is this pirate plot. You have in red and in blue. One is the control and the other is with the chipped pruned branches. But here you have some key information. You reduce from 4 to 1 the soil erosion. This means you have a field that has 4 tons per hectare of soil losses. In this case, it's 4 tons in 1 hour of 55 millimeters in 1 hour, which is a big thunderstorm, very intense. In the Mediterranean, is around a return period of 5 years. Here is around 10 to 15 years. Then is an intense thunderstorm that produces erosion. Then you reduce from 4 to 1. Just because it's an immediate effect. We are now studying plots that have many years of this system, how much erosion they have. Because we know that this is increase the biological activity, increase the amount of porous, reduce bulk density, then increase infiltration. Then, on long term, the effect should be even better. But we still need time to demonstrate that. This is the runoff. If you put in 1 hour 55 millimeters in 1 square meter, more than half move on surface. But if you have the cover of the branches, you have 34%. And one of the questions, we are moving more in my research group, probably because I'm getting older, and making all these measurements going to the field is very tough. We are moving to one thing that is, for me, very important, to ask the farmers. And then we went in different parts of Valencia, we selected areas in which we map the year where the farmers start to use the cheaper pruned branches. There are some farmers that don't use the white ones because they are very small plots. Sometimes it's 500 square meters. You don't contract or you don't buy your tractor for this. But the old ones, the big ones, see the big plots, they already 20 years ago they did because was, from the economical point of view, was very profitable. But there are farmers that they move to this because the subsidies, because the municipalities don't allow them to burn because forest fire risk, and because some they move to organic farming and they found that this is very positive. But there are many farmers that they don't use this because dirt. They consider that the cheaper pruned branches are dirt, the plots are too small, the parcel is too small, and then you don't buy a tractor or you don't rent a tractor for 15 minutes. And especially this, the farmers they say to me, I'm too old. I'm too old to change that. I'm more than 60, even I have farmers of 70, I have farmers of 80 years old. And they don't have somebody that will take care of the farm. Then they don't want to invest. Then we have all these situations, yes, no, yes, no. In general, it's moving to yes. In general, there is a trend that in few years there will be nobody that will not chop the branches because the labor cost and all these issues. But I have found farmers that they told me that this is dirt and they will never do because he will lose the prestige in the farmers community. I have seen farmers that they chop the branches. They make some pictures and they collect the cheaper pruned branches and they burn because they don't want to see there. Well, this is the reduction in, we are going to talk now, you see the previous picture, is somebody putting a straw. We can have the mulch there, like the cheaper pruned branches, or we can bring from outside some materials. Straw is very cheap. Many farmers gave to you the straw, you just need to put in bales and transport. It became a residue in some places. In the Valencia area, in the Albufera, in the lagoon, the straw of the rice, they will pay you to take it out. And then we make a research long time ago with Massimo, who is the guy that was in the previous picture, and we check all the publications that we have, and then all of them, they show that if you put a straw in the soil, you reduce immediately the soil erosion. And then we found this in different parts of the world. Spain is very important for this, in the United States, with China also. There are a lot of research on this, and always we found that was very positive. Then we initiate, after this review of the literature, we initiate experiments. We did rainfall simulations. We just put rainfall for 1 hour in a plot, one with a straw and one without the straw. And then when we do experiments and start the rainfall, we calculate from the start of the rainfall the time to ponding, when the soil is ponded, when the runoff start to move, and when the runoff reach outside. And then we found this, that if you have, for example, 60 minutes to have runoff or ponding, then if you put a straw, it's 3 times more. Then everything delay. Then this is very important for erosion. Delay the initiation of the runoff. And this is because the straw collects some of the rainfall and also avoid the impact of the drops, which is very important. The impact of the drops on the soil is the beginning of the soil erosion. The detachment creates a lot of sediments available. This was studied very well by the American scientists after the Dust Bowl in the 30s and 40s. Laws and Parsons were the 2 most important ones, and they studied the size of the drops, the kinetic energy, and they demonstrated that the impact of the rainfall is the most important, the drops. In fact, before the Laws and Parsons studies, the rainfall simulators, they would put the nozzles in the floor. And then after these studies, everybody started to put the nozzles on top because the drops need the kinetic energy. Then in all our studies, you will see here different study sites from different locations. When you have a straw, you have less runoff, less erosion. If you have a dissolver, you have more erosion. It's very simple. All these samples, this is the Montesa study site. Also, this was in orange plantations. The other, El de Vallada one is in olives. And then what we found is that this straw, chipped branches, really doesn't matter what you put there. If you put something organic that can be decomposed and increase the organic matter, activate the biological activity, then as soon you will have a cover with a straw or with whatever, then your erosion decrease. It jumped from, in this case, from 4 to 8, it just be around 1. It's very efficient. And then these are some examples of our soils that you need to refresh, to bring every year some straw. And this is the cover. After few months, is decomposed, then the soil is, again, it's clear, it's the soil cover. It doesn't matter if it's a straw or whatever. No? Massimo, that was a student that collaborated with me a lot, he did this review, and he found that you reduce almost 80% the soil loss and 25% the water, only in the first year. Okay, this is very clear. Then, one of the things that I have seen with our farmers is that they were obsessed to remove the rock fragments. The cover of rock fragments also is a cover. And then I have seen many years removing the fragments. And we did a research and we found that the rock fragments on the top are very good to infiltrate water and reduce soil erosion. Then we need to recommend the farmers to do not do it. If you can plow, I remember the old farmers with a mule or a donkey, a stone is a problem. But now with the big tractors, it's not a problem. But you know what? The European Union pay a lot of money the farmers to chop, to powder, to make dust the rocks, the rock fragments, the stones. In Italy was very famous this. And they developed machineries to do it. It was a big, well, we need to talk about the policies of the European Union were not always the best ones, okay? Well, how much straw do you need? We did research with different amounts of straw, bears, 5, 15, 30. Then if you have bear, you have this erosion. If you put 5%, half. Very important, put something on your soil. It doesn't matter if it's a lot of quantity. Well, we saw chipped pruned branches, straw, which is dead material. Let's go to see a live material. This is a vineyard in which the farmer is using cover crops for more than 20 years. He is organic, is following the Demeter rules, is having very good prestige and good income. And when we did the experiments, always very good. You have, when you have the vineyard covered, your vineyard is covered, runoff is almost nothing, erosion is almost nothing. If you use a herbicide, a lot of runoff and more erosion. If you use tillage, a lot of erosion and less runoff. But In one of our watersheds, in one of the regions that we study, we went farmer by farmer and we make a mapping of the management that they did, okay? Then almost 17% of the farmers, they use tillage. Almost 80% of the farmers of the land is affected, is used by herbicides. Catch crops, covered with oats, for example, is only 1.6 of the land. And straw mulch only was 0.1% of the land, which is one guy that is doing organic farming for long, and is using this. Then, what I told you until now is, herbicides is very bad. Tillage, also bad. Cash crops is very good, and straw is very good. But the farmers are doing them the other way around. They are using the worst management. I was very happy today when I listened that Andalusia is moving almost to 30% of the land into organic farming. Also, when I was listening Panos, he was talking about regenerative agriculture. I think we have a clear instrument in the European Union, which is organic farming. It's well established, it's very clear what is. Because what is regenerative, it depends who is in the field. Then, challenges. My experience. I'm bringing you here what is in my head about the future. First issue, long-term experimental research. We do not have this in Europe. I'm sorry, but we are far away from what the people from the United States did in the 60s. And then we are trying to develop policies based on sometimes in smoke. We don't have enough research. Especially we don't have enough basic research. Another issue is that farmers and landowners and workers in the field, for example, in Andalusia, I have seen many people from Africa working to harvest the olives. They also have a word to say. They are part of the future. And we really don't take care of this. We don't educate them. Most of my farmers, they use herbicides. A lot of herbicides. The soils are completely bare. It's like this soil. And we did not educate them. We did not inform them. Then soil health, this is a mistake, ecosystem health and human health is all together. When we see agriculture, we need to think in the health of the ecosystem, in the health of the planet, and in our health. And we are not focusing on that. Most of the farmers, they always tell me how many kilos of oranges, how many liters of wine, but nobody is focused in the quality. And then one thing, I'm sorry, I'm not a soil scientist, I'm not an agronomist. But when I see many talks of agronomists, probably most of you are agronomists. One of the key issues in the introduction is we need to save the world from hunger. We need to produce more food. I think we need to change this rationale. In Spain, in most of the farms that I work, 50% of the production is lost. In oranges, if it's too big, if it's too small, if it's not the right color. You know that every orange passes through a camera and they check the size, the form, and the color, and it's not fit, it's going out. Then 50% of the food do not reach our table. No? Then we can say that some farmers, the problem is that they produce too much. We need to think in how to produce healthy for the ecosystems, for the soil, for the planet, and for us. And then another challenge is the adaptation to climate change, which is, for me, it's difficult to see what we are going to do, because it's going so fast that my farmers, 30 years ago, they were working in August in the field, the whole day if it was necessary. Now it's impossible for them. Well, we need to design a future to enhance the soil, the landscape, and the people health. Some images of the experiments that we do, this is what we need. We need more experimental sites. In soil erosion, which is my topic, most of the research in the last decade is on modeling. And sometimes it's amazing for me because the modeling is almost without data. And then these kind of experiments is what we need. When I was talking about climate, this is one experimental area that we have for 14 years, is the annual rainfall here, the soil erosion per year, all the events. And you see, there was one year that there was almost no rainfall, almost no erosion. It depends on how much rainfall you have. And then it's going to change the temperature, the rainfall intensity. Then we need to study more. And I finished with one of these pictures. This is a picture that is almost 30 years ago of a farmer from a place that is called Font de la Figuera, 300 millimeters of rainfall, and he always grow the olives with cover crops. And then it's beauty. He understood that this is part of the beautiful part of the landscape, and you don't need... ¿Puedes pasar atrás una, por favor? You don't need to have the soil bare, okay? A ver. Una atrás, por favor, o dos? No, okay. Vale. This is the one I was telling you, that the actors are the farmers. The farmers can teach us a lot, and we forgot to make a relationship with them. In my opinion, we need to listen the soil, we need to listen the people, and just to bring home these ideas. It's the same that I told you at the beginning. Now you have more information to confirm or not this is true. Erosion compromises the health of the planet and the olive production. Agriculture is responsible for the soil erosion. We can do it well or wrong. We have strategies available. We can solve the problem, just we need to implement them. And if you are a scientist or a policymaker, don't forget to invest on science, on pure science, which is an issue that we don't talk, but we have not too much investment on science. United States still, even under the Trump administration, is investing more in science than Europe. And this should be not, and more things. Olive production is unique. When I come to Andalusia, I'm coming from China, I have been in Morocco, I came from the Netherlands, and when I come here, I see something unique. And you need to sell this unique landscape, unique product, and make it the best product possible. Okay, thank you.
Well, thank you very much, Artemi, for this outstanding talk. I think it's very, very insightful for everybody. So I think we have only one quick question, if anybody wants to talk something. So Tassos, perhaps.
Thank you. Great presentation. At the beginning of your presentation, you talked about forest fires. Is there anything we can learn from how recovery happens after forest fires are communicated to the growth?
Yeah. After forest fire, you have an increase in soil erosion, sometimes by 1 million. You need to prepare your land to have more runoff, more erosion. But we also learned that nature recover, and nature recover with more biomass, and especially with different plants. There is a floristic evolution, floristic composition evolution, and then this is what I have seen in the farms that where I'm working, that when you move from chemical farming to organic farming, the first year you have some plants, 5 years later the plants are different, and we see the ecosystem moving into a direction of a stable ecosystem. Then forest fires teach us this. And the other issue is that in forest fire we also can control the soil erosion, but it's very expensive. It's 6,000 to 7,000 euros per hectare, which is more than the cost to maintenance of most of the crops. Then I think we need to focus on improve our crops to reduce soil erosion. And forest fire affected land can be restored by themselves. In fact, what I see in forest fires is that the damage we cause in name of forest fires. Because there is a forest fire, we put machinery, we put caterpillars, we take out the wood, and then we destroy the upper part of the soil, we compact the soil, and then we have high erosion rates. But it's not because of the fire, it's because of our mismanagement. Why don't we invest this? We pay the farmers to make a cover crop in all the olive plantations. And I insist on that, not only paying them. We need to work with them. We need to collaborate with them. We need to teach them what we know, because they will teach us a lot that they know.
Can you hear me?
Yes.
Okay, good. Shall I start? Okay, so thank you very much for the invitation. I would like to talk today about soil health assessment and soil erosion research in olive groves across the Mediterranean. I would like to especially acknowledge my co-authors, Surya Gupta, who did all the soil health assessment quantitatively and figures regarding this, and Matthias Lang and Gabriela Moreno, who did the literature review and the figures regarding this part of the talk. So, as we all know, soil health in olive groves is not especially healthy for. It's not especially good. A lot of olive oil production is actually connected to low soil health. This, of course, is an extreme example from an organic olive oil production in Spain, where we can hardly talk about soil anymore. It's actually weathered bedrocks, but the olives grow in that. That it can also be very different is seen here in this example from Greece, where we actually from the Kefalonia island, where we have a different picture, a closed understory vegetation cover, closed ground cover, and of course less intensive production. Now, we were interested to see what is actually causing all the degradation in these olive groves, and can we assess soil health quantitatively, and how do we actually do that? We have currently a project running which is close to being published in JPNSS. You can already see the preprint on Research Square. It's called Soil Health Evaluation Rating Protocol and Assessment, SHERPA, which aims to assess soil health quantitatively. We are a big group of people throughout Europe, and the SHERPA key is really special because it really is the first real quantitative concept to assess soil health. So what we do is we quantify intrinsic soil health depending on land use. And of course, if I go out with students to assess soil health, what am I looking at? Well, in forests, I will ask for climate, geology, altitude, and humus layer, and I know whether the soil is healthy or not. In grasslands, I look at the fractional vegetation cover. In croplands, I look at fractional vegetation cover, soil structure, or percent of organic fertilizer to know what's going on. And actually all orchards and vineyards, so olive groves too, are assessed together with the croplands because we have very similar process and degradation factors there. But even if I have, which looks to me as a healthy soil, of course, I do not know anything about the pollution. There might be hidden erosion I don't see. So we have a part 2 to this. Oh yeah, the part 1, the intrinsic soil health, we score with a value from 1 to +10. Then we match this actually with part 2, soil degradation score. And here we assess all different erosion degradation processes, from erosion, landslide, heavy metals, nitrogen, phosphorus surplus, phosphorus mining, if any, pesticide input, salinization, compaction, and carbon loss or storage. And for each of these degradation processes, we have a table to score them from -1 to -9. So the most negative score for these degradation processes is -9. So if you want to know how we do this, the time is too short for that, then please look up our preprint. So if we add these two, the positive part 1 and the negative part 2, we would have theoretically the lowest number being a -8. So the lowest intrinsic soil health could be a +1. The lowest negative score for all degradation processes could be a -9. So this would get -8. So that you get kind of a scale. So we move from the total degraded soil -8 to the most healthy soil +10. Okay. Just to have a comparison, we did this for the whole of Europe with the Lucas data. You see here on the map, we divided between different European regions, and this is the distribution of points here. And here you have the frequency distribution between for the overall score. So part 1, part 2 added. And you see that 99% of all croplands in Europe score below 5. 85% below 2.5. Remember, the best value is 10, right? So doesn't look too good. If we look at single processes, we developed this cumulative score. So this is read like here we start with part 1. So the average for the different regions would be here around 3 for part 1, the intrinsic soil health. And then we subtract the single degradation processes. For instance, we subtract a -6 for the soil erosion. Then we have here landslide compaction. Compaction, we don't really have so good data, actually. Otherwise, this would be scoring more negatively, I'm convinced. But then what really contributes to negative scoring is nitrogen excess, phosphorus excess, then carbon assessment, and the pesticide risk. So if we look at the cumulative score in the end, the major threats are soil erosion, nitrogen and phosphorus excess, carbon loss, and pesticides. And the cumulative score differs a bit between the regions. So we have -19 for the northern European regions, -29 for central and western, and -34 for the southern. So how does this compare? How does it compare now to the olive orchards? And we evaluated the olive orchards of the Soil O Life project, the EU Horizon Europe project, for the upper soil. So here you see in the map, you see the distribution of the orchards. We have some in Portugal, some in Spain, some in Italy, and some in Greece. We do have some in Morocco, but we excluded that for this evaluation because the Sherpa is actually made for European soils, and I wasn't really confident to just apply it to Morocco, but we could look into that later. If we look at the distribution of the final score, so part 1, part 2 added, we see it looks a little bit different, a little bit similar to the croplands overall. With even some more positive than the croplands. However, if we look at the cumulative score here for the degradation processes, we see that we actually reach much more negative numbers than the croplands. So for the year now, it's average over the different countries. We have a -37 in Portugal and a -45 in Greece, Italy, and Spain. If we add up all these different processes, if we compare this again to the croplands of Europe, you see these are quite a bit higher, especially in the northern and central western regions. So we see that we have really a severe degradation overall in the orchards of the Soil O Life project. And the major processes are again soil erosion, nitrogen and phosphorus excess, carbon loss, and pesticides. However, there is a big but, and this but is actually the data availability. Even though this Horizon Europe has already acquired some data, we have to admit that for the site-specific data really measured in the orchards, we only had copper, salinization, SOC data, bulk density, and soil texture. For nitrogen and phosphorus surplus, we used literature data, what usually is used according to management type, traditional, intensive, or extensive use, or organic use, sorry. And for all the others, we actually had to rely on published maps. Now, part of these maps are kind of high resolution, which might be okay, but especially if you look at the pesticides, this is the Tang et al. Publication from 21, and we have a 10-kilometer resolution. So you will see later in the specific plot that we just have basically one value for each country because of this coarse resolution. So this actually we need to improve. But we can say that the general scoring, what we have here for the Sherpa values in olive groves, actually aligns well with our observations in the field. If we look at the Sherpa values across different countries, and here you have the number of olive orchards per country, we see that the part 2, so the degradation average of all degradation processes, is similar for Spain, Italy, and Greece, around -3, and for Portugal, slightly better, -2. Remember, the worst degradation is -9. However, this is a bit misleading because if you look at single processes, you really see that some of these processes are really reaching its worst limit. For instance, copper in Spain, Italy, and Spain and Italy is really a -9, which is basically the worst it can be. Slightly better in Portugal and Greece. Pesticides is really very high, around -8, with a slightly better in Italy. But remember the coarse resolution of our data. Nitrogen scores pretty negative, with Portugal very high nitrogen, followed by Italy, Greece, and Spain. Same with phosphorus excess, very high in Spain and Italy, and Greece, a bit lower in Portugal. And the carbon loss, of course, is really severe, and we will see the reason later when we look at the literature review. Sorry. Okay. So soil erosion, the last I show you here from this Sherpa values, is also, of course, pretty high. However, this is data from the modeling of the European modeling of Pasquale Borelli, and he will actually do an update with site-specific modeling towards the end of the year, which we will then update the data. But we see that we score here around -7 in Spain, followed by Italy, Greece, and then pretty lower, quite considerable lower rates in Portugal. The soil erosion, we looked a bit more in detail. Beyond the sites of the Soil Alive project, we did a literature review across the Mediterranean for these 4 countries. We evaluated around 80 studies. Here you see the publication rates over the year, and most of these publications, nearly 60%, are actually coming from Spain, followed by Greece and Italy. If we look at the study type, surprisingly, actually, most of the studies measured soil erosion, with only a third being modeled, and some actually did both. If we look at the methods, most erosion studies worked with runoff plots. Some assessed the mounds around the trees, actually, to assess the amount of sediments accumulated, and then a few other methods just used in single studies. Regarding the modeling, most were done by Russell, which is the most common model, with single studies with other models. Okay, if we look now at the soil erosion rates across the country, we see that actually, first of all, the measured and the modeled values partly are the medians of all study sites. The medians are fairly similar, except in Portugal, where we have higher values for the modeled than for the measured. But please note that we have very different axis scale. So from the investigated studies, actually, if we look at the upper quartile of all studies, we see that actually Spain has really a lot higher rates here, studies with very high rates. Sorry? Everything okay? Yeah, okay. followed by Portugal, Italy, and Greece. So these are very different access scales here. So we see what I showed you in the very first picture in this slide, in this little movie. Spain has really sites with really extreme erosion rates. Okay, we tried to do a small meta-analysis over these studies with trying to correlate soil erosion against precipitation, soil erosion against slope. We don't really see any clear patterns. We added as a third component the tillage regime, so conventional, no tillage, minimum tillage. This is just where we had no specification in the publication. We couldn't really see a clear pattern. We tried it differently, also in a three-dimensional plot with slope and rainfall against the amount of erosion here. And we see there's no clear pattern. Also, if we include the management type, again, conventional tillage, no tillage, we don't really see any clear indication for the reason of the high erosion rates. We looked at soil texture. No, this is for the measured values. This is for the modeled values. The soil texture triangle here. Also, we see no clear indication that soil texture. So what is the answer on soil erosion and olive groves for this meta-analysis of soil erosion study in Mediterranean olive groves? You would think it's tillage regime. So if we look at tillage, yes, we have the highest values with conventional tillage, but we also have studies with very low values. So if you look at the median here, the median of the conventional tillage is not really higher than minimum tillage. Then we have here studies which just gave tillage as a method, no specific information. So not really the answer. But if we look at the ground cover, there we really see a huge difference. So this is soil erosion in tons per hectare, depending on ground cover. Between trees and under canopy ground cover, we see we have very low erosion rates. If we have no ground cover, we have studies with extreme erosion rates, over 50 tons per hectare and 60 tons per hectare in year. And then we have studies where there was no information available on ground cover. We think that they probably also had no ground cover, but they also have very high rate. So I come to the conclusions. I showed you in the first part that soil health in olive groves of the soil or life orchards, we have a very low soil health in general, considerably lower than the average croplands in Europe. However, we have a low data availability for site-specific evaluation. So there we need to improve. Pesticides, copper, nitrogen surplus, phosphorus excess, carbon loss, and soil erosion are driving the low soil health. And the literature review on soil erosion across the Mediterranean showed that modeled values tend to be a bit higher than measured, but not overall. We had Spain having the highest values compared to Portugal, Italy, and Greece. The soil life data set with the Sherpa evaluations, we had a similar trend, a bit different, but Spain also had the lead in erosion rates. And soil erosion is driven by the removal of ground cover. I think this is shown again now. It's the main factor deciding whether we have high erosion or not. And with this, I would like to thank you for your attention and my co-authors for all their help and support. Thank you very much.
Thank you, Christine, so for this nice talk. I think we have time for one quick question, please. Yeah, Artemi and then Tassos. Two questions, Christine, for you. Can you hear good?
more than a question, Christine, it's just for you and for the audience. I think many people here from Andalusia, they know we are moving to a hyper-intense cultivation crops of olives. In the past, we have 50 trees per hectare. Now we have 2,000. And this is increasing the amount of fertilizers, amount of the use of water. And I think we need to have an eye of how sustainable is this new system, which can be very good for to make the olive oil probably cheaper, but not sure if the olive oil will be of higher quality. Then I think for the future we need to have an eye on this new strategy that is changing the traditional landscape. I'm not saying that it's worse or better, just that we need to check it.
There's a really strong echo, so it's really difficult for me to understand you. I don't know whether we can change that somehow.
Probably you can just.
Yeah, for some reason is. Can you hear me, Christine? Or still the sound is good? It's bad.
Yeah. Now I can hear you. Yeah.
Yeah. The question you got from the audience, from the Professor Cerdà, is that how do you think about the new modes of cultivation of olive oil for these huge plantations? Do you have any opinion to those questions? You're mute.
Yeah, I understood that whether I would have a suggestion how to manage intensive olive production, right, on these huge fields. And I think, is this the right question?
And also in related to this degradation index you have presented today.
Yeah, I mean, the second part showed clearly that soil erosion, and this will also, of course, have an effect on the carbon assessment. We need ground cover, right? I mean, ground cover, I think, is a very important part of the solution. And then, of course, we need to reduce pesticides. We need to reduce nitrogen and phosphorus. And I think we need really to think in that direction whether the olives even need so much phosphorus and nitrogen. This is not me to answer that, but I kind of doubt that. Then we already would have, if we would have already reduced erosion, nitrogen, phosphorus, and pesticides, I think we are already on a strong way. And I think part of these pesticides are probably also used to reduce the ground cover, right? I'm not sure whether these are only pesticides for pests or also herbicides included. I mean, the herbicides are included, right? So I think this is a lot of the answer.
Thank you.
I can answer the question related to previous comment. In the data that was shown, what was the distribution of traditional?
Could you maybe write the question in the chat quickly, whoever sits in front of the computer?
Yeah, I'm going to, because the sound is not good in the audience, I'm going to give to you. So see, he is asking to me, and I will pass to you, okay?
Okay.
Yeah. So Tassos is a professor from the University of Yale. Is asking about the distribution of the management in each country.
The distribution of
the farms, of the management type, at each country.
Okay, so the distribution of the orchard was shown in this map for the Sherpa assessment was in the soil life sites. We included all soil life sites in these 4 countries. And for the meta-analysis, we don't have a map actually. This was just all studies we could find. All studies we could find for soil erosion assessment.
Okay, thank you, Christine. Thank you for this nice talk and this advance of the soil project results. So very, very promising. Thank you.
Yeah, thank you, and sorry for not hearing your questions very well. This is, was unfortunate.
No problem. It's a problem we are having all the morning now. Okay.
Okay.
No worries.
Okay,
Bye-bye.
okay. So, see you.
Okay, let's move forward. Now it's time to, probably we are getting a nice picture on the diagnostic, and also we're going to talk about solution. Was Artemi also mentioned some of the solution, but now we have a solution from a more technological point of view, especially for copper and other pesticides.
Hello. Does it work? Yeah. Can you hear me? Yeah. Hello. Yeah, perfect. Good morning, everyone. Thank you so much for having me here today. It's an honor to be here in front. My name is Bryan from the University of Castilla-La Mancha. Today, I'm going to talk about one of the remediation techniques for contaminated soil. First things first. Can we combine electrochemical technology and environmental engineering? The answer is yes. That's what we are doing right now. Our group, the Electrochemical and Environmental Engineering Lab at UCLM, is working of combining like some different electrochemical technologies to treat gas emissions, soil, and effluents, including wastewater. Today, I'm going to focus this presentation on talking about soil remediation because it's the main topic of this conference. And, okay. So why do we need soil restoration? We still need to find the best remediation technologies. If we have a quick search on the literature, we cannot find the best available technologies for soil. We can find best treatments for water or for air, but for soil, we still need to develop some other techniques. Electrokinetic remediation is a physicochemical treatment, and it has some advantages and disadvantages as most of these techniques. For example, one of the advantages is soil structure and biodiversity is not really affected. You don't need excavation. However, we may need some long time to remediate contaminated soils, and also we need to monitor different parameters that can be quite tricky sometimes. But what's electrokinetic remediation? So briefly, we applied electric fields in soil by introducing two electrodes, one anode, which is positive, and one cathode, which is negative. So in this sense, we introduce electric fields from the anode to the cathode. And when this happens, we have some processes going on inside the soil. For example, water hydrolysis. So on the anode side, we have the oxidation of water to protons and oxygen. This creates an acidic front because we are generating protons. On the other hand, on the cathode, we have the reduction of water to hydroxyl ions. And in this case, we have a basic front. For some contaminants, especially for organic contaminants, this can be helpful because organic molecules can react with either the protons or the hydroxyl ions to degrade, and in this way, we can induce chemical degradation. Oops. We have some other processes as well. They are called electrochemical-driven processes. One of them is electroosmosis, which is basically the movement of water from one electrode to another electrode. Depending on the conditions of the soil, they are going to move, let's say, from the anode to the cathode or from the cathode to the anode. And if we go to the microscopic level, we have electrophoresis. When we have colloids or aggregation of particles, they tend to be charged. If they are negatively charged, they are going to go to the anode. If they are positively charged, they are going to go to the cathode. And we have now the molecular level as well. We have electromigration. In this case, it's similar to electrophoresis, but in this case, we have ions. Again, negative ions or positive ions are going to migrate to one of the electrodes. So these processes are quite important because in this way we can remove charged ions and soluble compounds in water. So we have plenty of contaminants that we can remove to those electrodes. And at the end of the day, we are going to end up with a low contaminant concentration zone, which is going to be the treated soil area. Now I'm going to focus about the operating parameters. The main one is current intensity, because those processes depend on the flow of electrons. So the first parameter that we have to monitor is current intensity. We have a real graph here, and as you can see, they normally tend to drop over time. And this is basically because we have ion depletion on the soil. At the beginning, we have, the ions are evenly distributed in the soil. But as they move to either the cathode or the anode, we are going to have some areas where we don't have ions, and that's going to increase the electrical resistance, and that's going to affect the process. Another aspect is soil drying. As electroosmosis happens, we are going to end up with areas with low moisture, so that's going to affect the movement of ions. Now we are going to talk about electrodes. The material of the electrode is also important. We can have a solid or hollow electrodes. Hollow electrodes are quite helpful when you try to recover those solutions, because the solutions are going to move to the electrodes, and because you have hollows, they are going to kind of get stuck over there, and then when you remove the electrodes, you're going to remove the electrode and the contaminants. And we also have the electrode arrangement, which is quite important. We have plenty of options here. I'm just explaining some of them. In the first one, we have a square arrangement. We have the anode and the cathode, a single electric field. We can also place an anode in the middle, and then we have a different variation of the electric field, and we can also combine them. Another technique is polarity reversal. So now we are changing the polarity. So the anode is now going to be the cathode, and the cathode is going to be the anode. That's going to increase the sweeping. That's going to increase the effectiveness of the remediation technique. That's going to redistribute the ions, which means that we are going to decrease the electrical resistance, and we are going to neutralize the basic and acidic fronts. In particular, I'm going to talk about chelating agents here, because when we have strongly absorbed contaminants in the soil matrix, we need chelating agents to help dissolving those contaminants. We have plenty of options, but the main ones are EDTA, EDDS, and some organic acids such as citric acid, acetic acid, and oxalic acid. So for chelating agents, we create an electrolyte chamber in the anode and the cathode, and we introduce the chelator over here. There is another option we have is permeable barriers. So basically, this is a barrier that's going to react with the contaminants. So you just introduce in the soil, and as the contaminants move from one side to the other side, they're going to get trapped. For example, you can use activated carbon, and contaminants are going to get trapped there. And then you just remove the barrier, and you're going to increase the decontamination. Perfect. So electrokinetic remediation is a dream technology or for lab research, or we can actually implement this. We can actually find several examples in the literature about treating industrial soils. We actually helped a contaminated site in the north of Spain in an industrial soil. They are actually pictures of our group. And in this case, we are not working anymore like with the small electrodes. We now have, as you can see in the second picture, 1 meter or 2 meter electrodes, which are in a way impressive. And the technology actually works. We demonstrated that we can remove up to 40% of the contaminants in 15 days, if I remember correctly. And as you can see, you don't need much. You only need electrodes and an electric and a power supply. So now, let's implement this technology for olive oak soils then. We have to identify the contaminants. We started focusing on copper, because one of the main fungicides for olive groves is copper oxychloride and copper calcium sulfates. They have some advantages. For example, they do not interact with plant leaves, and they are not soluble in water. However, they also affect the soil because they are going to tend to accumulate, especially on the surface horizon. And after they accumulate, we are going to have an issue because the fertility of soil is going to be affected. So we started measuring the concentration of copper in 16 orchards, and we found that the copper concentration is over 30 milligrams per kg, which is huge, because 30 is already too much. And as you can see in the graph, we even have one which is over 150. So that means that we actually need to implement technologies to remediate these soils. However, we have a huge drawback, because at the beginning we were like, okay, let's just implement them. However, we didn't have enough data in the literature. Most of the literature were focused on industrial soils or mining soils. However, we didn't find anything in agricultural soils. And this is important because, for example, in industrial soils, you are not really worried about what's going to happen with the soil afterwards, after the remediation. In agricultural soils, you need to consider that because that might affect the microbial activity, and the soil fertility can also be affected. So we need to study agricultural soils with this technology. And we started in the lab. Here you can see a small mock-up. We started with around 200 grams of soil, if I remember correctly. We had 2 graphite electrodes on one side, on the other side, and we analyzed experimental conditions such as the electric field and the flashing fluid. We started with the most common solvent, water. We added water in those chambers over here to see if we can remove the contaminant, if we can remove copper. However, nothing happened. At the beginning, we were a little bit worried that the technology is not going to work. And then we found that copper is strongly absorbed in the soil matrix, that when you flash water, nothing is going to happen because the absorption is so strong that water doesn't do anything. And we also check some parameters such as intensity, the mobilized volume, the pH, and the mobilized copper. So the first thing was analyzing electroosmosis. We did some experiments with chelating agents. Since we didn't manage to remove copper with water, we started with nitric acid and EDTA. And we found that electroosmosis was fine. So at the beginning, we were quite happy because we thought we are going to move copper dissolving water when we introduced those chelating agents. However, the reality was different. In the cathode, we didn't recover anything. And again, we were concerned about it. But then we measured the concentration of copper in the anode, and we found that with EDTA, the concentration spiked. And it was actually the only chelator that worked. And the reason why is that when EDTA and copper are together, they form a complex. This complex is negatively charged. And when it's negatively charged, it's going to go to the anode. And that's where we collect it. However, when we use nitric acid, this doesn't form this complex, and that's why we cannot remove anything. So this highlights the complexity to remove copper from this kind of soils. One of the drawbacks of using EDTA is that it's persistent, and it can create a problem in the environment. So we tested as a biodegradable chelator, which is EDDS. It has a similar structure. The main advantage is biodegradation. So we tested, and we found similar results, that they were not as good as EDTA, but they were similar. However, then we later analyzed the mobilization of copper with both, and we found that the applied current charge was higher with the EDTA and lower with EDDS. And that represents this is because EDTA has higher electrical conductivity than EDDS. So at the end of the day, in terms of electrical charge, both chelators use the same electricity to remove the same amount of copper, which is around 0.55 milligrams copper per applied current charge, which is good, because it's probably going to take a little bit longer, but we are going to use the same amount of electricity. So we defined that we can actually use this technology for agricultural soils, so we moved from the lab scale to a pilot scale. So in collaboration with some of our colleagues from the University of Jaén in Granada, we tested the technology in real mockups. So in this case, first of all, we need to change the power supply. Because at large scale, you need low voltage and low current intensity. But at bigger scale, you need a power supply with high voltage and high current intensity. And in addition, when you test this kind of technology, you are not going to use one electrical supply for each mock-up. That's going to be a waste of resources. So for this kind of remediation, you need to distribute the electrical connection. As you can see here, we have the power supply here, and the electrical connection is in parallel. One of the problems that we can find here is that the mock-ups don't have the same electrical resistance, because some can have a different concentration of ions, some other can have, I don't know, some other contaminants, the moisture is different, so that's going to affect the overall efficiency of the process. So we monitor this over time, and the main thing we did was analyzing the initial copper concentration in these mock-ups, and we found something astonishing, that the concentration was quite different. So in some mock-ups, we found copper, 950 milligrams of copper. Other ones have around 3,000, which is a huge difference. And we also analyzed the local copper concentration in those mock-ups, and we also found heterogeneity, like the variation was huge. As you can see, we have several examples over there. The concentration can go from 466 to 93, which is a huge difference. And that's going to affect the overall efficiency of the remediation technique. However, when we measure the final concentration of these mock-ups after 30 days, we found that mobilization actually happened. It happened from the anode to from the cathode to the anode. As we can see here in the map, we have this area, which is where the concentration is low, and we have this area where the concentration is high. So this is letting us know that we can actually remove copper from these olive soils. The problem is that we still need to analyze the impact on soil microbial activity. We tested the mortality of nematodes in those mock-ups, and we found that the mortality increases after the remediation time. However, the higher difference, we found it when you tested the anode, the center of the mock-up, and the cathode. The higher mortality was in the anode and cathode, and that's normal because we are changing the environment. We are creating an acidic or a basic front. But that's not the end of the world, because as one of the techniques I mentioned before is polarity reversal. So we need to study when we have to induce this polarity reversal to reduce those acidic and basic fronts. So overall, I will say that the electrokinetical remediation of copper-contaminated soils is feasible. And that's going to be one of the things we are going to try to implement in the future here in situ. And finally, I would like to thank our collaborators, especially Cristina Navas, who is the PhD student. She's the PhD student working in this project. She actually has a poster, and you can ask some more questions if you have any. Thank you so much for your attention, and thanks to the organizers. Yeah.
Have you shown the data for soil respiration?
Yep.
So, yeah. You have that?
Yeah.
Can we go to the presentation just real quick? So.
Oh no, wait. Soil respiration, we don't have it. We have
Nematodes.
Nematodes.
Yeah, soil respiration. Yeah, because here, and I know from this project, we are also evaluating not only nematodes, also it's a bioindicator, also the soil respiration is basically a proxy of the soil microbial activity. Okay, so I just was expecting a slide for that. Okay. So do you have any idea about that? Tell us.
The thing is, like, that's not, or I mean, we are working on the remediation on the mobilization of copper, since we are working in collaboration with some people from here. we thought that it's not going to be a good idea to present everything because they may be going to talk more about
In
it.
any case, we can talk later.
For Carboliva, it's a pleasure to assist to this conference in order to show the sustainability of the project. We are located very near from here in Puente del Obispo, and I will start maybe with a little index. I will speak at first with to explain you the oil sector in the industry way, and we continue to speak about the Carboliva, the first project that we have built, and the main thing is that when we when we put the soil, in the soil the biochar, we can capture the carbon. Okay. Starting to speak a bit, in order to introduce the oil sector, we have in Spain around 1,800 oil mills, but only 15 extraction plants. This production is 6 million tons of wet pomade, olive pomades. The more beauty of the sector, the well-known, is the extra virgin oil, but it's important to say that the extraction plants are necessary in order to solve like an environment problem, because you have to manage the water, the high content of the water of the mass. Of the fruit, the olive, you obtain in the olive mill the 20% of the extra virgin oil, and the rest of the mass is the 20% in weight. That you see here that the moisture content is very high. You have also the rest of the oil, only 2%, olive pits, and maybe 30% of olive pulp. The olives are harvested at the ground in the olive mill, where extra virgin oil is obtained, and the rest of the olive cake, which has a high moisture content, is centrifugated to obtain the olive pits. Is the first step. The mass is transported to the olive pomace extraction plant and is stored in waterproof ponds to prevent soil contamination with vegetable water, the alpecin. In wet form, they obtain the rest of the olive pits, and the cake has to be dried to extract the olive pomace oil. After the extraction process, they obtain the olive pomace oil and the dry olive pulp. The traditional way to do this dry process is burning the same biomass. You can choose between the olive pulp or olive pits, but this method is nowadays has a problem, a medioambiental problem. They use a rotary dryer, burning in an oven the biomass. They pass through some air in order to dry the mass, and they have to capture the little particles in the cyclones. But this system is not avoiding the whole particles, and now they have like pressure because some plants are near of some village, and their loads are each time more restrictive with the emissions. Another way to do it, because the majority have the traditional way to do the dry process, and the rest use cogeneration. They burn natural gas in a turbine or a motor, and they are generating electricity. The exhaust gases are used to dry the wet pomace. They have also like a restriction with the economic sustainable, because they depend of a subside of the government with the special regime that guarantees the profitable of cogeneration. And they started maybe 20 years ago, and in 1930 will end. Actually, some plants are stopping to dry the olive cake, because if the pool is low, the price is not profitable to them. In this sense, Carboliva is starting. The owner of Carboliva, the CEO, is Álvaro Espuny, is my father. He is the 4th generation and me the 5th of businessman in olive pomace sector. The project is aimed at solving a double problem faced in the Carboliva olive pomace sector. The economic, by transforming the peat and the dry olive pomace into biochar to provide clean thermal energy for the drying process of the olive pomace and other industrial processes, and solving an environmental problem by drastically reducing the dry emissions and waste caused by the traditional drying of wet pomace process. Transforming the biomass into biochar, we avoid to burn the biomass to provide the heat needed. Also, we found a new opportunity developing the biochar market, because we sell it, the material, and we can regenerate the soil and help to the climate action, applying the biochar in the soil. I will explain this because in the first project we used the heat to produce steam, not to dry the cake. I will also introduce you the pyrolysis process in traditional way. Here we see some photographs from Extremadura that they produce the charcoal production. You find this fume that is the syngas, because you have to start the process. They put inside the wood and start to burn it, but control the air in order to avoid flames. They normally know the syngas is like contaminating the air, and is not a modern way to do it, because you are just putting these gases into the air. We have developed a modern system with the rotary kiln. In September of 1980, Carboliva started the construction of his first pyrolysis plant. It's like a pilot plant through the agreement with Acesur Group. They have we have an expected investment of more of 5 million euros. The plant is located within Acesur production plant and olive pomace extraction plant in the town of Puente del Obispo. It's near to Baeza, and became operational in January of 2021. The plant consumes 15,000 tons in biomass per year and produces 5,000 tons of charcoal or biochar, while delivering thermal energy to the steam boiler with the power of 8,000 kilowatts. In the first project, we used the thermal energy to produce the steam because they have the cogeneration. In the past, they don't have the problem with the dry process. But Carboliva is planning to replicate the project and to use the thermal energy in the dry process. You can see here on a scheme, you introduce the biomass. At first, the kiln is cold, and you have to use a little natural gas in order to heat the inside the pyrolysis kiln. And at first you are producing the syngas and burning in a anchor. Okay, you burning it before to push to the air. And when you have stability in the production of the syngas, you change, because we have installed, at first the project doesn't has this installation, but we have installed an oxidizer chamber in order to burn all the syngas, and we are distributing using the heat, the exhaust gases, in order to feed the same kiln, and the rest of the thermal energy we pass through the steam boiler in order to produce steam. That the extraction plant needs this steam in order to separate the oil and the biomass. I will pass through there. You know the biochar, also because we are a little company and we have to research for the markets, different markets at first. we were using the biochar in order to do briquettes for barbecue, but now we are in the nowadays situation. Many markets are interested in the material because we have mainly both clients of industrial clients that consume a lot of volume, and they are using it in the metallurgy market in order to put inside the electric furnace in order to avoid the use of mineral coke, and they are avoiding to pay for the ETS, the emissions, more or less 3 tons of CO2. Although, yes, the idea of the project is to use to apply the biochar in the ground, in the soil, not only in agriculture market, because you also can use it to put maybe in gardens in the city, also maybe mixing in the cement or asphalt or new materials like activated carbon and that. We have the sustainability of the biomass. The origin is organic. We always have the same provider of the biomass, and because of that, we can produce like a very similar quality. We have reached recently the EBC certification. We are the first company in Spain to get this certification, and they are very, very exigent in order to get the right quality. You have to demonstrate with the analysis of laboratory that you complete the conditions, because you need to avoid the contaminants. An example is IHP, the hydrocyclic polymatic hydrocarbon, and also the ratio between hydrogen and carbon organic has to be below 0.4. We complete all of this. They also are studying our whole process with the life cycle assessment, seeing our emissions of the process from the beginning to the final point where we are applying the biochar. We also have a track system in order to demonstrate the transparency of the system, and they are also taking into account the emissions from the transport to the final point. When the client receives the material, they have to scan a QR code. The system calculates the full sequestration, because with the carbon organic content, we can take a sequestration of 2.5 in case of the olive pulp, and around 3 in the olive pits, CO2 of each ton, and many, because we get the certification with EBC and CSINC, and each certification has a different way to do the calculations for the carbon permanence. They rest in the factory gate 25% of the potential. They are very conservative, but they have to demonstrate that the carbon content is from many years will be no modified in order to avoid the emissions to the air again. You know, I'm not research, but you know the properties of the biochar is increasing use in the agriculture and soil amendment because it provides significant benefits. It improves water retention capacity, providing your plants with an extra water reserve and making them more resistant to droughts or sporadic watering. It retains nutrients longer near the root zone, which will boost tree growth. Increases the activity of microorganisms beneficial to the plants and improves the immune system of the plants. And the final result is improving productivity and health, more efficient use of water and fertilizers. The idea is also to reduce the fertilizer. because of the huge porosity, has this capacity of retaining the water. We normally are suggesting to mix with compost before to apply to the soil in order to increase the organic content. We have been doing the principal research. We participate in the soil olive. We have seen the presentation of the project. Also, Living Soil European project in olive trees. Resioliva project in super intense plantation, and also some private, like in Tecnova project in Almeria, we have do the research in tomato cultivation. These studies are still working, but the results are very, very optimistic. We need also to demonstrate, because we found like we are restricted because the agriculture men are in some way are very traditional, and they have to believe in the benefits of the biochar, because it's a cost for them, and we truly believe that is the future. But we are now finding some problems in order to get the enough market. Carboliva, as conclusion, is a traditional bridge, an innovation and a perfect example of sustainability and circular economy. Let's collaborate to restore soils and fight climate change together. Thank you.
Any question for Borja and Biochar?
We have done both trials, but we prefer, in order to avoid the erosions, maybe with the rain or the climate, in order to put inside the ground better. Because also we have done some trials in I don't know the exactly name in English, but it's like to put inside the bag and inside the ground in order to, it's like a house to take the water and also the microbial life. But yes, also to avoid the degradation of the emission of the carbon. Yeah, it's better to get into the soil.
How deep could be the best?
We have done the trials in half meter, more or less. You need like a machine, although is all the system are, the studies are like starting, and we are open in order to see the different results also.
Many thanks.
Yep. Thank you.
Its invitation for the conference. Well, I try to make a quick presentation because it's late. My speech is regarding the soil health and agricultural sustainability, and my aim is to present our results in several projects in the last years that show that the soil health is a good tool for to check and to test the agricultural sustainability in olive groves. Okay. First, I'm going to difference two terms that are confused in the literature and in the scientific ambit, because just to the 10 years ago, the scientific staff are speaking about soil quality, but in the last decades, in the last 10 years, the terms that has been imposed is the soil health. From my point of view, the soil quality and the soil fertility, that is the traditional terms applied to this problem, are both related or are both taking the soil from an external point of view. That is, the soil fertility is the capacity of the soil to supply the nutrients from the crop. So the point of view is external to the soil. No? In the case of soil quality, the soil that is defined as the soil capacity to sustain, to keep the ecosystem services, is also taken from an external point of view of the soil, but the soil health is the soil ability to function as a living system. So finally, it takes the soil from its own point of view. So I think it's maybe the main difference between the soil health and soil quality. Even though I will treat as synonym in my speech. Okay. Well, more and more research and specialists are taking currently the soil health as an essential component of course, of the agricultural sustainability, but also an essential component to achieve the sustainable development goals. So we have to take in account currently we have to take in account the soil quality, the soil health in this framework. Well, the question may be why the soil quality relating with another kind of components of the environmental quality, like the water quality or the air quality, why has been incorporated late for the scientific research, and maybe the question. For the answer may be the intrinsic complexity of the soil regarding the earth or the water. For the soil health, we start with soil properties, physical, chemical, and biological soil properties. Some of them, we can take some of them as soil health indicators. Not all the properties can work as good soil health indicators, so we have to select the best properties. In the meaning that some of these properties are strongly related, informed directly, rightly, about the soil function that is in the base of the soil health. So from the soil properties that inform the soil quality indicators that are proxies for soil function, and the soil function could foster all the ecosystem services, that is the benefits that an ecosystem provides to the society and improve the health, the economy, and the quality of life of the countries and the people. A healthy soil is one that guarantees a fulfillment of all ecosystem services, not only the agricultural productivity, but also for example, the climate change mitigation through the sequestering of carbon dioxide, but also the regulation of the water cycle, taking account, for example, the flooding risks or the drought risk, and so on. Well, as Panos this morning explained perfectly, the soil health is now in the European Union is encouraged. Is a field strongly encouraged because we have a lot of regulatory framework. The most important of that is maybe the soil monitoring law that fix as target that the most part of the degraded soil in the European Union will recover its functionalities performing for 2050. So, as the soil monitoring law explicitly defined, a healthy soil is one that meets the minimum level of thresholds for all the soil health or soil quality indicators. If one of these soil quality indicators don't achieve or don't attain the minimum level of quality, then the soil is in poor condition. And also, the soil monitoring law encourage to the government that they must certify the soil health and ensure the implementation of sustainable practices necessary to achieve these goals. Okay. Thereafter, for presenting my data, I will deal with three kinds of systems and to compare them. I'm comparing the conventional olive grove with the sustainable one, and also to take a reference level for both. I also deal with non-altered or little altered by the human being system, like a forest. Okay, in these slides I present one of the most important physical indicators of soil quality, that is the bulk density at 30 centimeters, and the average values for conventional, sustainable, and the reference values. So we can interpret that plot in the following way. In the red line marks the threshold criteria for the bulk density. That is, in this case, when the bulk density is the more is worse, or the less is the better. So it's not recommended that the bulk density excess in clay soil, for example, the value of 1.4 tons per square meter. So, as we can see, in conventional, the average values in conventional olive groves is close, or is just in this threshold, but in the sustainable and is lower, since we are comparing conventional plot with another conventional with another plot that are near, with all the physical and climate factors the same. We can the sustainable plot has at least 10 years of sustainable management, so we can measure in certain extent the effect in this more than 10 years of the sustainable practices regarding the variation of the soil quality values. That is the soil recovery. In this case, we can quantify 0.05 tons per square meter, the average recovery in bulk density due precisely to the application, the implementation of these sustainable practices. So we have to take in mind that the final target is to achieve the reference values, that is the value of the bulk density in the forest. Okay, in its European soil thematic strategy in 2012, the Commission fixed 9 soil threats that nine soil degradation processes that treat the soil health in Europe: the erosion, the soil carbon, organic carbon losses, soil compactation, landslide, soil saline, soil contamination, and that. We take this framework or this number of soil treats, and in one of current, I don't know why it doesn't work, because I think the battery is almost over. So in our current project, Living Soil, we have 15 experimental sites across all the Andalusia region, and we made a diagnosis of the main degradation process in each of these experimental sites. And we found that the main process, the main threats in the living labs, in the experimental site, was the low organic matter content that is always associated with a loss of biodiversity. Also, we have quite physical degradation, loss of soil structure and soil compaction that are always associated, soil erosion, water scarcity, and another kind of soil degradation processes. Okay, starting for the main degradation process that we found in the experimental site of the living lab. Really, we have soil organic carbon levels in the conventional olive groves that is below the recommended threshold of 1%. So it's a problem, but we can see that in sustainable olive groves it exceeds this threshold and is approximately half of the unaltered forest. As in the soil organic carbon is occur with other nutrients as the total nitrogen, the potassium, or also phosphorus. In the case of the phosphorus, the soil monitoring law taking account also not only the scarcity or the deficient levels in soil, but also mark a threshold for its excess in the soil. Okay, very related with the loss of organic matter is the loss of biodiversity. We can show the soil food chain, but in our project we focus in the microbes, in the bacteria and fungi. We have studied, for example, the enzyme activity. In this plot, we can see an average it's broken, definitively. Okay. In this plot, we can see average geometric mean of several soil enzyme activities as the phosphatase, glucosidase, adisulfatase, and the dehydrogenase. And we can see that in the conventional olive groves, the soil enzyme activity is lower than in sustainable one. Regarding very important, it's a critical parameters of biological soil health for the soil monitoring law, the soil respiration, is if we mark a threshold or 30 micrograms of carbon as CO2 per gram of soil and day. If we mark this threshold, the conventional olive groves are clearly below this threshold. But in the case of sustainable, we can recover and even pass this minimum threshold for soil basal respiration. Regarding the metabolic diversity that we analyze by means of the biolog ecoplates and very interesting technology, the metabolic diversity of soil is not measuring the taxonomic composition of the microbiome in the soil, but also its capacity to process and metabolize the several or the different sources of carbon. In this case, we can apply similar parameters as in the case of taxonomic diversity, the richness, and the alpha diversity, and we found that in every cases, in every parameter of the metabolic diversity, the sustainable olive groves were higher than the conventional one, and even if for some parameters the values of metabolic diversity in sustainable olive grove were higher than in the forest. This is a curious result. On the contrary, we don't find an effect of soil management, the type of management, regarding the taxonomic diversity. It was only or no effect or a very slight effect of the management in the taxonomic diversity estimated by metagenomics. So the most important, in this case, the most important factor that group or that can explain the variability, for example, in the beta diversity was the soil typology, mainly the soil parent materials, not the soil management that the human being carry out over this soil. Well, the solution that we are applying or we are studying for to recover the organic matter levels and soil biodiversity were mainly the cover crop seeding or spontaneous cover crop management, and also the organic amendments. Mainly the olive meal pomace co-compost, but we are also probing with or using the manure or even the biochar. Yes, we measure the quantity of nutrients that average cover crop in an olive grove can add to the soil, and is significant for not only for the nutrient but also for the carbon, the organic carbon that it adds to the soil. Okay, regarding the physical soil degradation processes, the physical treats. The first one was the soil compactation, the soil compactation is very associated with the loss of soil structure and porosity. And we have, actually, we have a serious processes of soil compaction, both in the surface of soil or in the subsurface of soil. In this case, is topsoil compactation, the surface compactation, as soil crusting. Okay, this is the soil crust that, as the professor Artemi Cerdà explained, occur by the impact of the raindrop over on the bare soil. The farmer needs, when its orchard is strongly crusty, the farmer know that he must tillage even more than 1, 2, or 3 times every year. So, with the aim to break the soil crust, but with every plow, obviously the soil is losing more and more organic carbon. This is a detail of the soil crust that can explain why a crusted soil can lose almost the 100% of water of the rainfall as runoff. The herbicides are also related with soil crusting. In general, every soil management that remove all the protection for the soil, and this is the problem of soil compactation regarding the erosion is that crusted soil are the starting point or the nick point of concentrated water erosion. In this case of rills, but the rills downslope can transform to gullies. We measure the two basic indicator, as the soil monitoring law said, for estimate the soil compactation. That is the ball density, but also the rod penetration resistance by means of a pocket penetrometer. Yes, the soil compactation is related with water scarcity, because if the soil loss is porosity, then they can retain less water. No? For our estimate, the olive grove soils can retain about a half of the non-cultivated soil, even taking account that the olive grove soil are about the double depth, depth of compared with the non-cultivated soil. This is equivalent, or this equal an annual supplementary irrigation of about 400 square meters per hectare. The solution for water scarcity is the same, or is similar to the solution for soil compactation. We are trying to, for example, we are testing the use of biochar directly applied to the soil, but also in the way of hydroinfiltrators. This is for our experimental site. For example, for the Almeria, the Vélez Rubio experimental site seems a vital, essential question, because they have a scarce rainfall in the last 10 years, an average of about 100 millimeters. So they have a problem, a critical problem of drought. In the case of soil erosion, we can evaluate in field the sheet erosion. The sheet erosion by its feature, the tree molds, the rock outcrops. In this case, it was a big tree mold. And of course, the rills. And we modeling the seed and rill erosion in our project, and we applying the Usle equation In this case, at the plot level, by means of remote sensing, digital elevation model, and using the GIS software, we can apply the usually high resolution at the plot level with a 1 meter pixel size, and we found that, as expected, the soil erosion in conventional plots was, of course, an average of 18 or 17 tons per hectare and years, and exceeds a lot the minimum threshold recommended. Not only the growth or the potential erosion in the plot, but also we can apply models of sediment delivery ratio to in order to test the production or sediment in bigger, at a lower scale. For example, in this case, is the high Guadalquivir River Basin scale, that is almost 200,000 hectares. And we can also explain the erosion, the inside effect of erosion, or why the soil erosion at the plot level can affect off-site all the basin for the reservoirs, for the river dynamic, and other bad effects or dangerous effects in the basin. Yeah, some more images. The crusted soil starting point not only for gullies, for rills, but also for gullies, and the gully growing down slope, and the effects in the orchard, in the olive grove, of the gully erosion, even with the loss of trees. Not only the small gullies in the slope are dangerous or affecting the olive grove, but also the big valley bottom gullies can make some dangerous effects in the borders of the olive groves. And relating the mega gullies, the big gullies, also are always related with another kind of soil degradation process, that is the landslide. As we can see, in this case, the farmer lost 100 trees in one night, in only one night, by a large landslide. And also, in this case, the rotational landslide are advancing upslope in the slope, and you can see the risk for the orchard. In the case of the last slides, we measure by means of photogrammetric techniques the incision, the ratio of deepening of this mega gully, this ravine, and we found more than 10 meters in less than 50 years. That is some erosion at the geological scale, not the ecological scale, of the human scale. We also take in account the effects of the infrastructure, for example, the rock culverts that are a red point or hot point to starting gullies, but they have some relatively easy solution, that is like the energy dissipator that could be installed at the continuation of the rock culverts. We also made some risk maps for gullies, a gully erosion susceptibility map that could be help the land managers to planify the land ordering, the land management. And the solution, if the gullies has a small size, we can use little geotextile or little modular blocks, like our colleagues of the University of Córdoba are developing, but also in the if the galley is a big galley, the question is that the control measures are very, very expensive. So it's almost impossible to achieve the budget to make this kind of project in all our extension in all the area affected by the galleys in the Jaén province. Yes, to make a summary, because I'm finishing, we measure 37 physical, chemical, and biological soil health indicators, including the soil erosion ones. In 25 of them, the sustainable values, or the values in the sustainable olive growth were higher or better than in conventional ones. In 3, even the sustainable values, or the values in the sustainable olive growth were even higher than in the reference points in the forest. In 20 of the soil indicators was a statistical significant effect of sustainable practices, and in 17 there was no significant effect. If we take all these soil health indicators and put together, we can give an index, a global index that's taking account all the effect of all these simultaneously, the effect of all soil quality indicators. We have two kinds of index. In one hand, we have a quick index to use in the field. This is based only in morphological properties, doesn't need analytical determinations. But if we put together, as I said, all the 37 analytic soil quality indicators in only one measure that is varying from 0 to 100. 0, you can understand 0 as the lower the soil, dead soil. Okay, and the 100, the reference value, the value of the unaltered forest, the ecosystem working at its maximum capacity. We can see that in about 10 or 15 years of application of sustainable practices, we increase almost a half of the objective or the target that the soil monitoring law establishing, that it recover for the European soil the maximum soil quality level, but this can affect that it is possible to achieve the European Union soil strategy goals, but of course it will not be easy. It will require an effort for the scientific staff, but also, or mainly, for the farmers. So, is our aims with all the research project, and this is all my that can.
Thank you, Julio. So unfortunately, we don't have time for questions. So if you want to talk to Julio, you can now catch him in the lunch. Okay? So he will be around. So are you staying in lunch? So okay. So you can talk to him now. So yeah. So because we are really behind schedule, so we're going to make a short lunch. Okay, it's something between 20 minutes and 30 minutes, okay? And then come back for the next session. Thank you.